Binomial probability is something that's derived out of the binomial theorem. If you recall, the binomial theorem is a way to expand a binomial taken to the nth power. It's the sum of a bunch of terms, and within each term there are three parts. The first part is the coefficient, which is n choose k, or combinations of n things taken k at a time. That's calculated right here with n factorial over n minus k factorial times k factorial. Then comes the product of our two terms in the binomial. Notice that the sum of their powers, n minus k and k, would always add up to the nth power. Let me show you how that works with x plus 5 to the third power. Let's expand this using the binomial theorem. So we would take the sum with k starting at 0 and going up to 3 of 3, choose k, then x would be to the 3 minus k power times 5 to the k power. When we expand that, we start with k being 0. So our first term is going to be 3, choose 0, x to the 3 minus 0 power times 5 to the 0 power. Then we let all those k's increase by 1. So in our next term, we're going to have 3 choose 1. X is going to be to the 3 minus 1 power, which is 2, times 5 to the first power. And as we continue, notice we'll go 3 choose 2, and then in our last term, it would be 3 choose 3, the two x's. As we continue along, notice the x power started at x to the third, then x to the second, our next one would be x to the first, and our last one would be x to the 0. And the 5's increase in powers. So 5 to the 0, 5 to the first, times 5 to the second, and lastly times 5 to the third. Now comes all of the calculating. 3 choose 0 is 3 factorial over 3 minus 0 factorial times 0 factorial. X to the third, and 5 to the 0 is 1. Next term, 3 factorial over 3 minus 1 factorial, so that's 2 factorial times 1 factorial. Okay, and notice this, x to the second, 5 to the first. Those match up directly with the denominator that we're calculating as our initial coefficient. So in the next one, we'll have 3 factorial over 1 factorial, 2 factorial, and then x to the first and 5 to the second. And then the last one, 3 factorial over 0 factorial, 3 factorial. X to the 0 is 1, and then 5 to the third is 125. Now as we calculate a little bit further, we notice in these fractions the 3 factorials are going to cancel. 0 factorial is 1, so our initial coefficient here is 1 times x to the third times 1. And the next term, 1 factorial is just 1, 2 factorial is 2, and 3 factorial is 6. So 6 divided by 2 is going to give us 3. And we'll have 3x squared times 5. In the next one, we have the same fraction, so our coefficient will still be 3, x times 25. And in the last term, notice fractions is the same as what we began with, so we'll have 1 times 125. So we real quickly clean everything up, and this expansion is x to the third plus 15x squared plus 75x plus 125. So that's how we use the binomial theorem to expand an entire binomial. Now, obviously, with something like x to the third, we could have some easier ways to go about it, but as that power increases, having the binomial theorem becomes very helpful. As we extend that to the binomial probability, that's going to be the likelihood of success in n trials with two possible outcomes where the probability of success in each trial is the same each time. So it's that two possible outcomes that is our binomialness. Those are going to be the two terms that make up that initial binomial. And the n trials here, that's going to be the power of our binomial. So if we're looking at a situation where a family has 3 children, with each child there's two possible outcomes, that child is either going to be a boy or a girl. So we can set up a binomial as boys and girls. And since they're having 3 children, that would be to the third power. Now we can use the binomial theorem to help us find the probabilities of having exactly 3 girls. We do that by expanding b plus g to the third. And with the binomial theorem, start with 3 and 0. So b goes to the 3, girls go to the 0. In our next term, it would be 3 choose 1, b goes to the 3 minus 1, and g goes to the first. The next term, 3 choose 2, b to the first, g to the second, and the last term, 3 choose 3, b to the 0, g to the third. Simplifying each of these, we end up with just 1 b to the third plus 3 b squared g plus 3 b g squared and 1 g to the third. Now, seeing this entire expansion is actually kind of clever, because what we see is all 4 different possible situations. The first term represents that situation where all 3 of the children are boys. In the second term, we have a situation where we have 2 boys and 1 girl. The third term is 1 boy and 2 girls, and the last term is a situation where all 3 are girls. Now, with those 2 middle terms, since they have a coefficient of 3, what that 3 represents is the 3 different ways that you could have 1 boy or 1 girl. So considering that second term where we have 3b squared g, that girl could have been born first, could have been born second, or could have been born third. Those are the 3 situations. In this case, what we want to look at is the probability of having 3 girls. That's right here, g to the third. How we will calculate that is just by inserting the probability of having a girl. And since having a girl is equally as likely as having a boy, that probability is 50%, or 0.5. And 0.5 to the third is 0.125, meaning that there's a 12.5% chance that a family with 3 children would have all 3 of them be girls. Let's look at another more complicated example. At Jenny's telemarketing job, 15% of the calls she makes result in a sale. If she makes 20 calls, we want to find the probability that exactly 5 of them will result in a sale. Now, this is a binomial situation because each time that she makes a call, there's 2 possible outcomes. She could either make a sale or not make a sale. And the number of trials is going to be the number of times that she makes a call. In this case, we have 20 calls that she's making. Now, trying to expand this binomial would fill up pages and pages to go through all the work and come up with our 21 different terms. Now, the thing is, we don't care about all 21 of those terms. We only care about one term in particular, and that's the one where exactly 5 of them will result in a sale. So the term that we're looking for is going to have exactly 5 sales, which would mean that there would be 15 of them that are not sales. So our coefficient for this term would be 20, choose 5. So we can just zero in on that one particular term to speed this process up. So to calculate this, we're going to use 20 factorial over 5 factorial and 15 factorial. Our sales to the 5th and our not sales to the 15th. Now, we're told that 15% of the calls she makes will result in a sale. So for our sales probability, that's where we'll put in 0.15. And our not sales probability then would be 0.85. And really, at this point, you got to use your calculator to help you out. And when we calculate all of this, we end up with 0.1028, which means about 10.2% of the time she'll get exactly 5 sales when she makes 20 calls.